This study focused on the thermal envelope of a building, which plays an important role in controlling heat transfer between indoor and outdoor environments. One of the main challenges in building is excessive heat transfer through the wall. High heat gains increase the cooling loads, causing HVAC system to consume more energy. As a result, electricity cost increase and overall energy efficiency decreases. In addition, conventional building material may not provide sufficient thermal insulations, leading to greater heat penetration into the building. To address this issue, expanded cork is proposed as a sustainable insulation material due to its low thermal conductivity. It can reduce heat transfer through the building envelope and improve thermal performance. The main goal of this study is to enhance building energy efficiency, reduce HVAC energy demands, and support SDG 7 by promoting more sustainable and efficient energy use. Okay, this slide I will explain why expanded cork insulation is selected and how it relates to SDG, affordable and clean energy. Firstly, expanded cork is a natural and renewable insulation material with low thermal conductivity. This property helps reduce heat transfer through the building envelope, resulting in better thermal performance and lower energy consumptions for cooling and heating system. In addition, expanded cork is environmentally and friendly, making it a sustainable choice for modern building. And secondly, SDG 7 focuses on improving energy efficiency and promoting sustainable energy use by reducing heat gain and heat loss. Expanded cork help minimize energy waste and support the implementations of energy saving technologies. Therefore, the use of expanded cork not only improve building energy efficiency, but also contributes the achievement of SDG 7 by supporting sustainable and responsible energy consumptions.
Okay, in this slide, we are analyzing a wall cross-section under steady state heat transfer. On the left, intense exterior heat at 45 degrees Celsius pushes thermal energy against the structure. To block this heat, the wall utilizes 3 layers that are each 100 mm thick. The first line of defense is an outer concrete layer with a thermal conductivity of 1.0. Sandwiched directly in the middle is our primary thermal barrier, a layer of expanded cork. This core acts as our main insulator due to its exceptionally low thermal conductivity of just 0.0385, which drastically slows down the penetration of heat. Finally, the wall concludes an identical inner concrete layer, also featuring a conductivity of 1.0 to provide a structural support. On the right, the interior air is kept at a comfortable and cool 20 Celsius, driven by a significant 25-degree temperature difference between the environments. The heat naturally flows from the hot outside to the cool inside. Our main objective here is to calculate Q, the heat flow rate per unit area, to evaluate exactly how effective this cork insulation is at maintaining a protected indoor climate. Next, let's take a look at our data material table for the wall cross-section. We have organized the properties of each 100 mm layer to show why this design works. Our outer and inner layer are made of concrete with a density of 2000 kg per meter cube and a thermal conductivity of 1.0. However, the magic happens in our middle layer, which is expanded cork, because it is highly lightweight at just 120 kg per meter cube. It has an incredibly low thermal conductivity of 0.0385.
Next one, for the calculation of total thermal resistance R value. So we have 3 layers of wall, which is exterior concrete, expanded cork, and also interior concrete. So for concrete, we use because of the same material, we use the same formula and same data, which is thickness divided by thermal conductivity times area. So we put all the data together, 0.1 divided by 1.0 times 20. And for expanded cork, 0.1 for the thickness over 0.0385 for thermal conductivity times 20, which is area. And then for total thermal resistance, R total, we sum all of it, R1 plus R2 and plus R3, and which is will give us the final answer 0.1399 Celsius over watt. Next one, for calculation of total heat transfer coefficient U value for expanded cork. We use the heat transfer equation, which is U value times area times temperatures difference equals to temperatures difference over resistance. We can cut the temperatures difference, delta T, from both sides, and then which give us only U value times area equals to 1 over resistance, and then let the U value alone there. So put the area on the other side. So the final equation is U value equals to 1 over resistance times area. So we put the value together, which is 1 over 0.1399 times 20, and the final answer will be 0.3574 watt over meter square Kelvin.
Cycle, me, Diana, I will explain the calculation the loss head. We are analyzing the thermal performance of well station for startable body project in the picture. We have selected expanded cork as our isolation material. First, the formula for the head loss is head loss will equal U value material multiplied surface area of the material and multiply the temperature differ between the inside and outside. So they are give the value for our area is 20 square meter, temperature is 25, U value meter is 0.3574. The answer we get is for the head loss 178.7 watt. So the value of 178.7 watt mean in the real world scenario is first energy flow. First is represent the rate of the energy transfer. This means the exactly of the thermal energy is passed through our 20 meter wall where every single circle drift by the 25 temperature difference. Secondly, HV watt particle trigger have our cooling system the method of controllable indoor temperature. The air conditioning system must continuously work to remove this watt of the heat gain for the room. Lastly, high efficiency. For the cyber recipe, this is very low and efficient value. It proves that our choice material is better called efficiently low heat transfer. By keeping this value low, we significantly reduce the body energy demand, which save electricity and lower our overall carbon footprint. Now, let's compare the thermal performance of head brick wall and conventional brick wall. Both wall we are analyzing use the same condition, and the result show that head brick has a much lower U value of 0.3574 compared to 5 for the bright, indicated better insulation performance. As a result, the head loss to the head brick wall is only 178.7 watt, while the brick wall lose 2,500 watt of heat. In addition, April has a higher R value, which means it provides greater thermal resistance. In calculation, April significantly reduces heat loss and offers much better energy efficiency than the diurnal break wall, making a more sustainable body material.
SDG 7 focus on ensuring affordable and clean energy, and expanded cork support this goal through its excellent thermal insulation properties. Cork has a low thermal conductivity value, approximately 0.037 to 0.040, which means it slows down heat transfer effectively. From our heat transfer analysis, a higher R value indicated better resistance to heat flow, resulting in lower heat gain into the building. This directly reduces the cooling load required by HVAC system. When the cooling load decreases, the HVAC system does not need to work as hard, which leads to lower electricity consumption and improved energy efficiency. Therefore, expanded cork contribute to reducing energy usage, lowering operating costs, and decreasing carbon emission. This clearly aligned with SDG 7 by promoting sustainability and energy efficient building solution. In conclusion, expanded cork is an effective insulation material that performs better than conventional brick in terms of thermal resistance. Its higher R value and lower U value significantly reduce the rate of heat transfer through building wall. Based on the heat loss calculation, this improved insulation reduces the amount of heat entering the building, which directly lowers the energy demand for air conditioning system. As a result, the HVAC system consumes less electricity, improving the overall energy efficiency of the building. This leads to reduced operating costs and lower carbon emission, making expanded cork a sustainable and environmentally friendly material. Therefore, it is suitable for energy efficient building design and strongly support the objective of SDG 7 for clean and sustainability energy usage.